Planetary Gear Set. A simple planetary gear unit, viewed from its delivering end. Dual roller bearings, at the output help isolate the gearing from the effects of external transverse loads. The heavy disk is the planet carrier. Planetary gearing, with its inherent inline shafting and cylindrical casing, is often recognized as the compact alternative to standard pinion and gear reducers. Being suited for a wide range of applications, from electric screwdrivers to bulldozer powertrains, these units are strong contenders when space and weight versus reduction and torque are chief concerns. The arrangement. The most basic form of planetary gearing involves 3 sets of gears, with different degrees of freedom. Planet gears rotate around axes that revolve around a sun gear, which spins in place. A ring gear binds the planets on the outside, and is completely fixed. The concentricity of the planet grouping with the sun and ring gears means that the torque carries through a straight line. Many powertrains are comfortable lined up straight, and the absence of offset shafts not only decreases space, it eliminates the need to redirect the power or relocate other components. In a simple planetary setup, input power turns the sun gear at high speed. The planets, spaced around the central axis of rotation, mesh with the sun as well as the fixed ring gear, so they are forced to orbit as they roll. All the planets are mounted to a single rotating member, called a cage, arm, or carrier. As the planet carrier turns, it delivers low speed, high torque output. Planetary gearing. Planet gears, for their size, engage a lot of teeth as they circle the sun gear, therefore, they can easily accommodate numerous turns of the driver for each output shaft revolution. To perform a comparable reduction between a standard pinion and gear, a sizable gear will need to mesh with a rather small pinion. Simple planetary gears generally offer reductions as high as 10:1. Compound planetary systems, which are far more elaborate than the simple versions, can provide reductions many times higher. There are obvious ways to further reduce speed, such as connecting planetary stages in series. The rotational output of the first stage is linked to the input of the next, and the multiple of the individual ratios represents the final reduction. Fixed axis gearing, pinion driving. Since planetary gears mesh with the sun gear and ring gear at several locations, more teeth are engaged to drive the load, compared to a conventional gear and pinion mesh. Therefore, for the same load, planetary gearing requires smaller gears than a standard pinion-to-gear reduction. Likewise, the radial arms of the planet carrier transfer substantial moment to the output shaft, another illustration of the efficiency of a concentric arrangement. Perhaps a less obvious, but no less significant consideration is that with multiple, equally spaced planets, the input and output shaft bearings are spared the radial loads resulting from separating and tangential gear reaction forces. Because these reactions cancel out. Plus, since no such forces act on these bearings, there is less potential for distortion of the outer casing. With more planets comes an increase in load capacity and torsional rigidity. The more divided the load, the less deflection and wear of gear teeth. It follows that quite a large load can be driven in a comparatively small and streamlined planetary gear unit. 3 is typical for the number of planets, but there are often more, and sometimes less. Again, it is common for multiple planets to be equally spaced. Planet balancing. The load taken up by the planets is, in real situations, not perfectly balanced. One planet might by chance end up radially closer, or further than the others from the sun axis, or the axis of the carrier rotation might be slightly off. As the precision of manufacture goes down, and the number of planets goes up, the tendency for imbalance increases. Sometimes the effect of an imbalance is small, and the operation is able to accept it. The planets might even wear in and gradually engage the load more evenly. But some designs will be sensitive even to slight imbalances, and may require high-precision components and assemblies. Pinpointing the proper locations of planet pins around the axis of the Sun gear could be the key. Noise. In planetaries, noise is usually no worse, and often better than standard gear and pinion reducers. Having smaller gears means a lower pitch line velocity than a comparably rated pinion and gear set. However, having a lot of identical planet teeth engaging at the same frequency, with each input shaft revolution contributes to noise, especially at very high speeds. And the fact that these meshes occur in a circular orbit can make the situation more complex. Obviously, using spur gears of reasonably high quality couldn't hurt. But helical gears, with their gradual rather than instantaneous tooth engagement, might be better for some operations. Heat. A planetary gear train running at very high speeds and continuous duty is apt to generate enough heat to justify cooling. With ordinary gear and pinion systems, the load often requires quite a large chunk of gearing and surface area, which amounts to an appreciable heat sink. The compactness of planetary units can limit the rate of heat dissipation, and therefore additional measures are sometimes taken. The lubricant may be circulated through a heat exchanger, or a cooling fan is employed. If the operation is continuous, the system has less opportunity to cool than if it runs intermittently, and without sufficient cooling, the speed allowance might need to be lowered. Or, as mentioned, other kinds of speed reducers can be attached ahead of the planetary reducer, although this is an added encumbrance.